You're welcome in today's session at Medical Sciences. And today we want to discuss about different isomers of glucose, or what we call sugar. We see that monosugars exist in different isomers. And what are isomers? Isomers are molecules with the same formula. They have the same molecular formula, but they differ in structural arrangement. So we are saying isomers are compounds or molecules with the same molecular formula but different structural formula. Those are isomers. And we see different sugars, especially glucose, existing in different forms. The structural formula is the same, the molecular formula is the same, but there is a difference in the arrangement of the structure. And as we get started, we remind you to subscribe, like the video, and share to the many. And as we begin, isomers, or what you are calling isomerism of sugars, or what we are calling glucose, in regard to glucose, we are going to see different structures. And among the isomers of sugars who have the same molecular formula but differ in structural arrangement, they include, whereby we shall look at keto Aldose isomerism. We shall look at the D and L series, and these ones we call them Enantiomers, which is a type of stereoisomer. Then the third one, we shall look at the Anomers, or what we call Anomers. These Anomers show Anomerism. Then number 4, we shall look at the optical isomerism in the presence of a plane polarized light. And the last one, we shall look at epimers, which portray epimerism. And we're going to discuss them in details. So keto Aldose, which is one of the first isomers of glucose, we see that glucose having the same molecular formula, that is C6H12 then O6. This is all of them have the same molecular formula, but we are seeing them differing in the structural arrangement, whereby glucose, and this one I'm going to call it D-glucose, whereby D-glucose, I'm calling it D because if this is carbon number 1, number 2, 3, 4, and 5, the hydroxyl group at carbon number 5 being on the right, we call it D series, which is type of Enantiomers. So this is D-glucose. But this D-glucose with the aldehyde as a functional group, that's why we call it aldose sugar. So this one becomes aldose sugar, but when we change the functional group from carbon number 1 to carbon number 2, it becomes a keto. This one is a keto sugar, then this one is an aldose. And this one, despite of it having the same molecular formula, we see this one being D-glucose and this one being D-fructose. It becomes the fructose due to the change in the position, whereby in the glucose where we have the aldose, it becomes a ketone. It has an aldehyde functional group. This one has a ketone functional group. But others remain the same, whereby here we shall have OH, OH, then H. Others remain the same. That's why we're calling it D-fructose, differing in the position of the functional group. When the functional group is at carbon number 1, it is an aldehyde, and when it goes to carbon number 2, it becomes a ketone functional group, and that is the difference in this type of isomers. And examples, we have seen D-glucose and D-fructose as type of sugars portraying keto Aldose isomerism. Number 2, we are going to look at enantiomers, which we call D and L isomerism. And these isomers, we are saying that these enantiomers, what are enantiomers? Enantiomers, it is a type of stereoisomers or stereoisomerism, whereby the two different compounds are mirror images. that if I put a mirror image, if I put here a mirror, this one being a mirror in the middle, we are saying that these two compounds become mirror images of each other, but are not superimposable, or they cannot lie on each other. It is like the right hand and the left hand. The right hand and the left hand, they are mirror images of each other, but they are not superimposable. They cannot lie flat on each other, but they are mirror images of each other. And these are the ones that we call enantiomers. And examples, we have the D-glucose and L-glucose being enantiomers, which is a form of stereoisomers. Stereoisomers meaning they are mirror images of each other, but they are not superimposable. So we are saying that these guys are stereoisomers. These ones, they show stereoisomerism. Why? Because they are mirror images of each other. So that if I have this glucose, if this is OH here, and this one is OH, this one is H, and this is OH, we're going to see forming the mirror image of this, whereby this one at carbon number 5 will remain the same, but we see at carbon number 5, the OH group which is on the right goes to the left. It becomes this. Also this one goes to the left. Then this one, the H which was on the right, on the left, goes to the right. And this one goes to the right. So these ones are what we're calling mirror images. So we are going to see that this glucose number A and B, they are mirror images. So these ones are mirror images of each other. They are mirror images. But we are saying they are mirror images, but they are not superimposable. They are not superimposable. They cannot lie on top and they lie flat on each other. Like the left hand cannot lie on the right hand. But they are mirror images. They are the same but different. They are the same, or they are the same images but different. That's why you're calling mirror images, but non-superimposable. So this one, after doing this one becomes D-glucose. This one becomes D-glucose. Then this one becomes L-glucose. Why? Because how do we distinguish D-glucose from L-glucose is at position number 5. When the OH group at position number 5, or the hydroxyl group at position number 5 is on the right, that one is D-glucose. Whereas when the hydroxyl group at carbon number 5 is on the left, if it is on the left, that one becomes L. Left starts with L. And when it is on the right, at carbon number 5, it becomes D-glucose. This one becomes D-glucose, this one becomes L-glucose, due to position of the hydroxyl group at carbon number 5. Whereby here it is on the right, we call it D-glucose, and here the hydroxyl group at carbon number 5 is on the left, we call it L-glucose. So these are the D and L series which show enantiomers, and we call them type of stereoisomers because they are mirror images but non-superimposable. So these are enantiomers. Mirror images, don't forget that they are mirror images but non-superimposable. And they differ at position number 5. Then number 3, which we can talk about in this session, is anomers. And anomers, these ones are portrayed by cyclic or ring structure according to Haworth projection. That when this one, the hydroxyl group at carbon number 5 interacts with carbon number 1 to form a cyclized ring, this cyclized ring, if we put a plane in the middle, and carbon number 1 is always known as the symmetrical carbon atom, or we call it anomeric carbon atom number 1. This anomeric carbon atom If the hydroxyl group at carbon number 1 is above the plane, if it is above the plane, we call it beta glucose. When the OH group at anomeric carbon, if it is above the plane, if I put a plane in the middle and I find the hydroxyl group at carbon number 1 is above the plane, that is known as beta glucose. But if I draw another one, if I have another one and I find that the hydroxyl group and I put a plane in the middle, I find that the hydroxyl group at carbon number 1, which is an anomeric carbon atom, is below the plane. So here we are calling it beta glucose because the hydroxyl group at carbon number 1 is above the plane. It is above the plane. We call it beta, and here we call it alpha glucose when the hydroxyl group at carbon number 1 is below the plane. So this is what distinguishes between alpha sugar and beta sugar. Beta sugar, the hydroxyl group at anomeric carbon atom number 1, when it is above the plane is beta, and when it is below the plane, and even this one is always portrayed by the way we write them. You see, when I'm writing beta, I go up, and when I'm writing alpha, I go out. I go down. So how do I know that beta, the hydroxyl group is above the plane, is when I'm writing beta, I go up. So I know it is above the plane, and when I'm writing alpha, I go down, meaning the hydroxyl group is below the plane. So science is very interesting. So this is what we can distinguish between different anomers, that is alpha and beta glucose, existing as anomers. Why they are anomeric, they differ at anomeric carbon atom number 1 or asymmetrical carbon atom, whereby when it is above the plane beta, below the plane it is alpha. So another thing we can talk about is number 4, which is optical isomerism, and this one applies in a plane polarized light. So when I have a solution, and this solution maybe contains D-glucose and L-glucose, these guys have optical activity. What is optical activity? Optical activity of a substance is the ability of this substance to rotate either clockwise or anti-clockwise in a plane polarized light. That if I have a solution and I put a plane polarized light, and these molecules in the solution, they have the ability to rotate either left or right, that is what we call, we say that those molecules have optical activity. So we normally see D-glucose and L-glucose, they portray optical activity whenever they are subjected to a plane polarized light in an electric field. That if we have a solution containing D-glucose and L-glucose and we subject it to a plane polarized light, we see some of them, if this is the center, we see some moving in clockwise direction, some they rotate, some rotate in the clockwise, they rotate on the right, and other molecules, if this is the starting point, other molecules rotate on the left. And those that rotate on the right, we call them dextrorotatory, and they are always denoted by a positive sign. And those that rotate on the left, they are known as levorotatory. And how do I always remember is that this one which is rotating on the left begins with L, and even this one begins with L. And this is how I can always remember that those molecules that rotate on the left, they are known as levorotatory, and those that rotate clockwise are known as dextrorotatory. And the ones of levorotatory, they are denoted by a negative sign. So this one is clockwise, they are rotating wise, and these ones are rotating anti-clockwise. And when they rotate, if one is rotating on the left, another one is rotating on the right, and where they meet, they cancel the charges. And where all of them are equal in number, and where they meet to cancel the size is what we call a racemic mixture. So we are saying if these guys rotate and reach and they meet here, and also this one rotates on the left and they meet at the same point, the negative charge and the positive charge cancels out. And here at this point, they have no charge. And at this point where they have no charge, where they meet together is what we call a racemic mixture. This one we call it racemic mixture, or you can call it a racemic solution. And here there is no charge, whereby both the D and the arrow have the same number and the charge cancels out, and we call it a racemic mixture. So this is what we call optical isomerism with substances like D and arrow glucose, which exhibit optical activity, that when we subject them on a plane polarized light, some move clockwise, that is dextrorotatory, and they are positively charged. And those which move anti-clockwise, that is on the left, they are known as level rotatory. And always remember that because left begins with L, even the word level rotatory begins with L. And as we end, we want to end with number 5. And this number 5 is epimerism. This is the glucose molecules that portray as epimerism, and we call them epimers. And what are epimers? Epimers are substances. We are going to see that epimers are substances. Epimers, these are substances that differ. They differ at a single. They differ at a single asymmetrical carbon atom. Single asymmetrical carbon atom. So they differ at a single, in the arrangement of the hydroxyl group, at a single asymmetrical carbon atom. And an example is when I have D-glucose. D-glucose, I want to focus on carbon number 4 and carbon number 2. So we shall see that D-galactose is an epimer of this one. D-galactose is an epimer of glucose. Is epimer of glucose at carbon number 4. Whereby if I have everything the same here, everything is the same. This is carbon number 5. Here it is number 4, number 3, number 2, number 1. We're going to see others are the same except at carbon number 4. So this one remains the same. This one remains the same. But they are differing at carbon number 4. Whereby at carbon number 4, if glucose, the hydroxyl group is on the right, this one is on the left. So we see the hydroxyl group at carbon number 4 shifting on the left. When it shifts on the left and the hydrogen goes on the right, these ones become an epimers. We are seeing they are differing in the arrangement of the hydroxyl group at a single asymmetrical carbon, that is carbon number 4. Whereby on glucose, the hydroxyl group at carbon number 4 is on the right, then the hydroxyl group on the galactose is on the left. And these ones are called epimers. So that's why we are saying galactose is an epimer of glucose at carbon number 4. Whereas D-mannose, for it is an epimer of glucose. This one is epimer of glucose. This one becomes epimer of glucose at a single symmetrical carbon number 2. So this is at carbon number 2. This one is at carbon number 4. whereby others are the same, like glucose, they are the same. But we are saying here it is on the right, we shall find this one migrating on the left. So others remain the same, they remain the same. But at carbon number 2, we are seeing the hydroxyl group, which is on the right of glucose, shifting to the left. And we shall see it coming on the left. And the hydrogen, which was on the left, goes to the right. And we end up by saying that mannose is an epimer of glucose at carbon number 2, whereby the hydroxyl group, which is supposed to be on the right for glucose, is on the left for D-mannose. So they become epimers of each other. So in summary, we can see the galactose and mannose are epimers of glucose at carbon number 4 for galactose and carbon number 2 for mannose. So they differ in arrangement at a single asymmetrical carbon atom, whereby we have seen number 4 is for galactose, whereby the hydroxyl group changes the position, whereby if it is on the right here, it goes to the left. And I'm seeing here even when at carbon number 2, the hydroxyl group, which was on the right, shifts to the left. And this is what we call epimers, differ from each other at a single asymmetrical carbon atom. So thank you so much for being with us, where we have discussed all types of isomers in glucose, whereby we have talked about keto aldose isomerism. We have looked at enantiomers, which are mirror images but not superimposable. And the example was D-glucose and L-glucose. L means left, the hydroxyl group at carbon number 5 is on the left. Then D means on the right at carbon number 5. Then we looked at anomers, whereby they occur in cyclic structures that if it is above the plane is beta, and if it is below the plane, the hydroxyl group at carbon number 1 is below the plane, we called it alpha glucose, whereby when you are writing alpha, you go down. Then we have looked at optical isomerism, which we gave examples of substances that show what we call optical activity. Either they rotate on the right, that is dextrorotatory, or on the left, which we called levo rotatory. And we said when they are moving or when they are rotating, where they meet, we called it a racemic mixture. Then we have ended up with epimers. Thank you so much for keeping up to date until the end. Thank you so much.